Welcome to Academic Digest class. In today's class, we're going to be treating energy stored in a capacitor. Whenever you hear energy, I've proved it to you in our first semester class. Always think of it as work. Always think of it as work done. And you need to know that whenever you think of this work done, you always think of potential energy. Potential energy and kinetic energy, their formulas are the same thing. One is half mv square and the other one is mgh. But when you check the dimension, you see that those two things will give you the same dimension. So if I know this, if I have this in mind, I can now go on to treat capacitor. First of all, energy stored in a particular system is simply given by, that is in electric field or in electricity or electric circuit. Energy is simply gotten from this formula, which is potential, electric potential is equals to the work done in moving a unit charge. So this thing now can be the same thing as saying PE, like Q. And also the same thing as U. We use this U to represent this over Q. So this is the place you get the relationship. So normally, if you want to get this work, you say is U equals to VQ. So work done is equals to VQ. And we normally say that this will be a negative, it will be in negative direction, if you remember. Or when it has to do with capacitor, let's say this is your capacitor. Let's say this is voltage, this is battery. So this is work done in electric circuits, this one. So but remember that what we are doing today is not work done in electric circuit, but work done in capacitor. In as much as a capacitor is a device that stores energy or that stores charge. So if I know this, let's say this is our capacitor and this is our voltage. So you can see that if we supply, let's say this is the positive part and this is the negative part. If we supply this particular charge, now if we are supplying energy to this capacitor or to this circuit, the work that this charge will be able to move here because work will be done. It will move from this point to this point to this point to this. So the points, the positions are different positions. So we normally say that the energy stored in a capacitor is equals to the charge or is equals to the work done in supplying it. So if I use this battery to supply 5 let's say I supply 5 microfarad or maybe 5 coulomb of charge, and the work done is like 12 voltage. By the time I remove it, what I've supplied is what will be there. I see it, and I can recover it when I connect maybe another maybe capacitor and it gives charge to it. So I can now say that it is recoverable. Like I can recover it when I allow this capacitor to discharge. So enough of the long story, because that's not what we are here for, but I just want you to understand the concept. So if I know this, we simply say that since the work done, the moving charge in a capacitor is not at a place, we will now carry this now. We'll say that U, which is work done, will be in such a way that it will have change, because so the work is not steady, so it changes. The work done in moving this charge, it changes. So I have change equals to the V, and the charge that I'm supplying is Q. So you see it is this way. So which means that if I want to make V subject of the formula here, is the setting that's saying that V is equals to change in work done all over change in Q. So but we remember that from Q equals to CV, this is actually the relationship between voltage and charge and then capacitor. That is the capacitance. Why this is the relationship between voltage work done and charge. So we are going to be comparing these two relationships. That is what we are going to be comparing. So notice that if I have this now, this is going to be this one now with the same thing as saying V is equals to Q over C. So we are going to compare these two. Let's say I call this equation 1. So I call this equation 2. So let me substitute this for V so that I now have change in U all over change in Q is equals to Q over C. So I just substituted this one for V. So when I do that, I will now see that making work subject of the formula, because that's what we are doing, energy in a capacitor, or in work, or energy in capacitance, energy stored in a capacitor. That's what we are doing. So I want to make work subject of the formula. And remember, work is not just work. There is not at a point. The position varies. So I now have change in work. This is change in work is equals to Q change in Q all over C. You will see some textbooks where you have this to be. If you compare these two things, you have something like maybe Q square, that is this now, all over C. This is not wrong, but when it has to do with capacitance, it is wrong. Because in capacitance, you have to take it that it means change in Q here. And when you now say it, anytime you have something that is moving from one particular position to another position, you introduce the integral sign so that you have delta U is equals to integral of Q delta Q. And this thing is something that's saying charge with respect to charge all over C. So that I now have, you might see some textbook come and put this as a definite integral, meaning running from 0 to Q. If you want, don't put it. So delta U, and yes, so I'll put integral sign here as well. So I'm integrating both sides so that I can remove this changing. So this is something as an integral of 1 with respect to U. So you see that if you integrate 1 with respect to U, it just becomes U is equals to integrating this now, Q with respect to Q. Go and check my video on integration. So the same thing as saying there's 1 here plus 1, so Q square all over 2. This will be 1 plus 1, 2, divided by the new power. So if you do it, then remember that it's having C here, then C. Another way to look at this is that it's the same thing as saying 1 over C integral Q naught then Q delta Q. So if you do it, you see that this is now the same thing as saying Q2 over 2 then 1 over C. So another way to look at it. So this is what I have. So if I know this, notice that this is a situation where I have charge and capacitance. So when I'm given charge and capacitance and I'm asked to find the energy stored, I can easily use Q square over 2C or 1/2, this is half Q square over C. So when I'm giving charge and capacitance, so I normally tell my students, classify this as for QC. For QC, when you are giving charge and capacitance, and let me not put this here, just when, let me do it here, giving charge and capacitance, to find, let me write it this way, to find energy when giving charge and capacitance. This is the formula. This formula we have here is what you use. But when we want to find energy in a capacitor, when giving capacitance and voltage. So when we want to find this when given this, we can simply say, since we've gotten that U from U equals to half Q square over C, we can remember that Q is equals to something. If you remember, we can remember that Q, so from Q equals to CV. So we can come here and replace Q here with CV. So we can say 1 half CV square all over C. So U is equals to half C square V square over C. This will cancel this. So that we have that U is equals to half CV square. So you need to note this as well. So notice it's U is equals to 1 half Q square over C. You need to note this as well. Oh God, what are you doing? Smart. So you need to note this. So this is the first one. The second one. Now when you are given, or when you are asked to find energy in a capacitor, when given charge and voltage. So if you are given this, you now need to remember that from U equals to half CV square, that U is equals to half, this is the same thing as saying C V times V. And notice that these two things means Q. Q is equal to this. So U is equals to half Q, and then this V. So you need to know this. So you see it. So altogether U is equals to half Q square over C. Comma half CV square, comma half QV. So you need to note this, or let me do it this way. So you need to note this. So you can write somewhere where U equals to energy slash work slash potential energy. So if I know this, these are the basic formulas to calculate energy stored in a capacitor. But there are special cases, like when I'm talking about maybe electric field or energy stored in space, or I'm considering the, let's say, parallel plates. So I can now relate this. So I can say energy stored in a capacitor, or say in a parallel, let me say in a parallel plates capacitor due to electric field. And I want to believe that by now, once we talk about electric field, something comes to your mind. That is Gaussian theorem. So Gaussian theorem, that is G. If you remember GEX, we said GE. That is this for Gaussian theorem. Electric potential charge. If you remember, the other one was surface density, right? If you remember when we started, so surface density, but this time around the S part is not what we're going to be having. We have now voltage, charge, and so instead of C we will now have instead of S we now have another C. For this case it will now be capacitance. So Gaussian theorem. So if I'm comparing, I will compare Gaussian theorem to V, to Q, and to C. That is to voltage, to charge, and to capacitance. You know that the relationship between electric potential and electric field is V equals to E R. I normally use R for distance, while the relationship between charge and this one is equals to, if I have Q equals to C V. Capacitance is related to them by saying C equals to Q over V. Okay, so let me now remember that I said Gaussian theorem. I will relate Gaussian theorem to these three parameters up here. So because if you've noticed, once you're talking about capacitor, these key things, electric potential, voltage, charge, and capacitor, they play a lot of role. So but whenever I want to find electric field, I talk about Gaussian theorem. So now saying relating Gauss law to voltage, I have first of all EA is equals to Q over E naught. And I know that E is equals to Q over E naught A. Yes. So if I know that, I now need to remember that if that is the case, if I'm relating this now to V, relating it to V will now be the same thing as saying from V equals to ER, can now say V is equals to, put everything for E here, Q over E naught A times R, that is distance. R equals to distance. Some people use D, me I like using R for my distance. So then let's go again. So I've noted this one. This is the first thing I need to note, the first one for relating this to electric field. Now, relating Gauss law to charge, which is Q. And now that this is going to be EA equals to Q over E naught. If you remember, that's the theorem. Therefore, I'll now have this to be, let me do it here. I'll now have this to be EA times E naught. I'll use dot equals to Q. So the second one. Now, I noted that. Now relating, remember we said that we relate Gauss law to these three things. So relating Gauss law to capacitance, so we can be able to do that by saying EA is equals to Q over E naught. Then we need to remember from should be from E equals to Q all over E naught A. Yes. We remember that V is equals to ER. If you remember, I'm just reminding you what we've done. I'm putting it to one side so that we can get the relationship with capacitance. ER. Then that means that V is equals to Q over E naught A. Are you seeing it then times R? This is relating V to E. This is relating V to Gauss law. If you remember. So if I know that, but I remember that if I'm relating capacitance to the three parameters, I normally say that Q is equals to CV. So remember, Q equals to CV. That means that V is equals to Q over C. So I want to replace V here with Q over C so that I can be able to have C that I will use to relate to Gauss law. So that I now have Q over C is equals to QR over E naught A. So I've replaced this V with this. So CQ here, CQ here. Let's see it. So I will now have I now have 1 over C is equals to R over E naught A. So cross multiply, I now have CR equals to E naught A. Divide both sides by R, divide both sides by R, this will get out. So that I now have C is equals to E naught A all over R. So by the time you've done this, we now have energy stored. So we now have, therefore, we have V equals to QR over E naught A. We have Q equals to EA dot E naught. And we have C equals to E naught A all over R. Then we remember, so we say, we now have to compare this. We now have to compare what we've gotten here to what we have for energy stored in a capacitor. So we now say, remember, U is equals to half CV square. So for that reason, U will be equals to half C is this. So E naught A over R. Then V is this. QR over E naught A. So all squared. So you can see that this will now mean that U will be equals to half E naught A over R, then times Q square R square over E naught square A square. So if you want to carry this now and times this, you see that this will mean the same thing as saying, first of all, times this will cancel this, and this will cancel this, and this will cancel this. So we now have that U is equals to half Q square R all over E naught A. And notice that Q, remember that we are comparing Gauss law to what we have for energy stored. So we are trying to derive energy stored in a capacitor or in a parallel plate capacitor. We are trying to use Gauss law to get that. And the result is always something that will lead us to electric energy density. So now that we've gotten this, we have Q. Notice that Q here is equals to EA dot E naught. So we now have that this will be the same thing as saying half EA E naught all squared, then R all over E naught A. So I will turn to finish up. I'm out of space. Okay, but let's try. Let's try to do it here. So I now have half E square. I'm squaring everything here. Half E square, E naught square, then R all over E naught A. Remember that this is half, and anything half goes to the 2 before you. So this will take care of this. Shall we? Yes. And there's A here. So look at this. This is A. So there's A that will be squared as well. So this A will take care of this as well. So we are now left with half. Now left with U equals to half E square. Then we have E naught, then A R as our final answer. So we have this way. So let me write it this way. Let me come here. So I'm now saying U is equals to half E square E naught AR. But notice something. Please ignore this. Notice something. A is area, and area is in meter square. R is meter. By the time you do meter square times meter, it is meter cube, and meter cube is volume. That means that everything I have here, that means that this is volume. So that means that this is volume. So for that reason, I can say, because what we are trying to derive here is energy density. So I can say divide both sides by AR, or you say divide by volume. So that means that this will be U over AR is equals to half E square E naught AR, yes, divided by AR. This will cancel this. So that I now have U over AR and is equals to half E square E naught. And I want you to note something. Anytime you have something over volume, it means density, or you say volume density. And anytime you have something over area, it means surface density. And anytime you have something over length, it's more or less linear density. You need to have that in mind, even if it has another name. Just like when we do surface tension, you know that thing is the same thing as saying force or linear force. So if you know that, you can now say that everything you have here, this is energy, work, and this is volume. So we'll call this, we say that this is energy, electric energy density. So this is a law, and this law states that electric energy density on any surface, even if it's not parallel plate capacitor, is directly proportional to the square of electric field. So multiplied by permittivity of free space and half of it. So half of square of the electric field, half of square of of electric field, and that is half of the product of permittivity of free space and square of electric field. So if you know this, that's our final answer. So what we did here is we are able to use Gauss law that talks about anything electric field, you need to relate it to Gauss law in most cases. So we're able to use it to derive this equation for electric energy density. So go through it over and over. I believe it will make sense to you. So in our next class, we'll now take time to solve questions.